Hello again. In our previous video we used the optimizer in the PlanOpSim Metacell software to optimize for a thin film structure. In this next example we'll take this a little bit further to use a nanostructure to make a stronger anti-reflection coating than is possible using thin film materials. So it's a well-known issue of homogeneous films that in order to get the best theoretically possible thin anti-reflection coating behavior, we would need a lower index material than is available. Nanostructures and effective media offer a way out of this option by changing the structure and in that way creating effectively a lower index than of the bulk material. So to do this optimization, we will create a new example that I will call a pillar optimization. Voilà. And we will go and set up the exact same structure as before. So a silicon dioxide substrate with an air top layer. But in this case, we will add a structure which is not homogeneous, but a circle structure. And I'll set the pillar here as well as the name and create the height variable like we did before. So a new variable which has the type optimization. Its name will be height, starting from 1 to 500 nanometer in steps of, not with steps, but with the starting value 2. And store that here. I'll reduce the size of the unit cell in order to be sub-diffraction for my working wavelength of 550 nanometers. So I'm setting this to 350 nanometer. And my pillar will be made of fused silica as well. Since we're now optimizing both the height and the shape of the structure, we can select here the radius and make this also an optimization variable. So new variable of optimization type, name radius, and let's start this one at 25 nanometer radius up to 100, for instance, in steps with a starting value of 50. Well, actually we can go up to 150 with 150 with no trouble here. And store that. Okay, so we have our structure set up, we have our two variables, and we can go on, like in the previous example, to define the targets. Go to Metacell targets. We modify our optimization type from a sweep to the Bayesian optimization algorithm, like so. Save that. We're still fine with 100 evaluations, and we here under the incident light again modify our target. We still are not too bothered about the phase, so we can remove that target parameter and we can just focus on the transmission height here, the power transmitted, and target 1. Under simulation settings, we now have our two height and radius variables, and the accuracy we will keep at the default 4x4 now, because we now have a structured material, so a large enough accuracy is needed in order to have accurate simulations. And we can go back to the simulate view and launch the simulation on the server. So this is now already a little bit more of a extended optimization using two parameters. If we would do this with brute force sweeps, it would take us a little bit more time already as well. But let's let the optimizer run for now and see which results we find. Simulation went to running now. Don't worry if it gets into the queued status for a little bit. That's the process of sending the simulation info to the server and starting the calculation. So now that it has progressed to running, our calculation is being done. Voila, and now that our calculation has run, we can once again analyze it by looking at some plots or exporting the data. So we will add a plot here, and in this case we will still keep our sweep variables at the various axes. So I'll set the height to the y-axis and the radius to the x-axis, like so. And for the color of the different scatter symbols, I will select the power coefficient in the 0, 0 order and update this plot. Oops, I've made a tiny mistake here. I would like to see all values, not just the best value like I had previously selected. So instead, I will just use all values here under optimization variables and click update again to post-process this. And there we go, our optimization has completed, and we now see a scattered list of our different configurations that were simulated. And as we expected, there are again interference fringes, multiple bands of height here, which will result in better total transmission. But I'd like to zoom in here on the lower height over here, where we indeed see a region around this between this 110, 130 nanometer radius, where we have the maximum transmission. And actually, if we inspect the values, you see that indeed for this wavelength, where we can get it, the effective index and the height simultaneously tuned, we get expected transmission values of 99.9% and above, so well above the restriction that we had using just homogeneous films. This is one of the examples of how a nanostructure can be used to create effects that would not be possible with bulk materials. And there are many more, but this should give you a first hint of how you can use the PlanOpSim software to optimize for the behavior of nanostructures. If you have any questions, feel free to reach out. Thank you very much.